Hello and welcome to this film about gas stoichiometry. It's actually the first in a series of 4 films which cover Year 12 calculations. This isn't all of the Year 12 calculations, but it kind of takes you up to the Semester 1 exam. It covers all the Stage 3A stuff that isn't covered in those 8 films that you might have watched before this. Okay, so by the end of this film, hopefully you'll have had some practice doing a few different types of calculation that use this formula, PV equals nRT, and maybe a few other gas rules along the way. Okay, let's start with the first one, and you might remember this being mentioned when we were looking at empirical and molecular formulae. So sometimes you might have calculated an empirical formula and then you need to know the molecular mass or the molar mass to find the molecular formula. Well, here we're being asked to find the molecular weight of a substance. So this is that kind of a problem, I suppose you could say, right? We're being asked to find big M. Now we know that a formula for little n is m over big M, right? That means that we know that big M is equal to little m over n. Okay, how does that help us here? Well, we've got little m there. That's a mass of substance, okay? But the rest of it is P, V, and T. So this looks like we're going to have to use PV equals nRT. Alright, and if I rearrange this, I can actually see that N is equal to PV on RT. Right? And if big M is equal to M divided by N, then therefore big M equals M divided by PV on RT, which is the same thing as M multiplied by RT on PV, or in other words, MRT on PV. So in other words, if I know the pressure and volume of a gas and its temperature and its mass, I'll be able to find its molar mass. Okay? M, big M, that is, the molar mass is equal to the mass times the gas constant, blah, 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 blah. Alright, so let's do the calculation. Okay? And that means that capital M, the molar mass, is equal to the mass, so 20.83, multiplied by the gas constant, that's a number that we don't have to remember, it's on our data sheet, times the temperature, but that's got to be in Kelvin. Okay, so I'm going to add 273.15 to that, and make that 303.15, and all that lot is going to be divided by the pressure times the volume, so that's 79.97 multiplied by 4.167. Okay, and if you do that on your calculator, you get an answer of 157.5. So every mole of that substance weighs 157.5 grams. All right. So there's one kind of use for PV equals nRT that we'll see in Year 12. Here comes another one. And in fact, this one uses the fact that the volume is proportional to the number of moles. Why does this use that? Well, we're told the volumes of 2 gases, and we're given a mole ratio from an equation. But we can remember, hopefully, that if you're doing all this at the same conditions, then if you know the mole ratio, then you know the volume ratio. This means that every 2 litres of hydrogen will need 1 litre of oxygen. Okay? In actual fact, I've got 3.72 litres of hydrogen and 2.35 of oxygen. All right? So this one you might be looking at it and thinking, oh, PV equals nRT, but I don't know a load of stuff. It's all done at the same conditions. It doesn't matter what the conditions are. We are using the fact that the volume is proportional to the number of moles if we keep the pressure and the volume and the temperature the same. Okay, so anyway, here we are. Every 2 litres of hydrogen should have 1 litre of oxygen. So in other words, 2 litres of hydrogen should use half that amount, which would be about, what's that, 1.86. So this needs 1.86 moles of oxygen, but there's 2.35, so that's less than 2.35. So in other words, the oxygen is in excess. Okay, therefore the oxygen is in excess, and that means that our hydrogen is the limiting reagent. All right. How did we know this was a limiting reagent question? Well, we looked at it and we weren't told the masses of two of the reactants, but we were told the volumes of two reactants, and we were told to find this. Okay, so anyway, here's our limiting reagent. We're going to base the amount of product on that, except we don't have to find the product in this question. We're being asked to find how much excess is left over. Okay, so I'm not sure if I just pointed at this as our limiting reagent. This was the excess. Okay, this needs 1.86 of this to react, so we're going to have 2.35 minus 1.86, and that is equal to 0.49 litres. Okay, so that's a gases problem, but we don't have to use PV equals nRT there because everything's done under the same conditions. So we say that the mole ratio is like a volume ratio. Okay, last example calculation for this film. Okay, we've got we're given some volumes and temperatures and pressures, so it looks like PV equals nRT. Okay, different conditions for the two gases. This one's at STP, so we can save ourselves a bit of hassle here. We can actually use that, or we can remember that 1 mole at STP occupies how much? Hopefully remember, 22.71 litres. That's changed. Okay, that used to be measured. STP used to be given on your data sheet at 101.3 kilopascals, so there was a slightly smaller volume there. Look out for that if you're doing practice problems, because you can get a slightly different pressure to what's used these days. All right, but anyway, let's go ahead and do this. 200 litres of H2 will require how many litres of O2? Well, we've got a 2:1 mole ratio here. Can't use that volume ratio because we're doing it under different conditions. Okay, but we do know that the number of moles of hydrogen, okay, is equal to twice the number of moles of oxygen. We're actually being asked to find the number of moles of oxygen and the volume, so the number of moles of oxygen is a half of the number of moles of hydrogen. Can we find the number of moles of hydrogen? Yes, of course we can, because N equals PV over RT. So the number of moles of hydrogen is equal to, what's that? We've got 150 multiplied by 200, and we're dividing that by RT, 8.314, our friend from the data sheet, and T, which is now 298.15. That's a multiplied sign, 298.15. Okay, do that sum and you find that the number of moles of hydrogen is, where are we, 12.1 moles. Okay, and therefore the number of moles of oxygen, which we decided was half of that, is 6.05 moles, and therefore the volume of oxygen, so how many litres, the volume of oxygen, which is going to be the number of moles times the molar volume, because we're at STP, so that equals 6.05 times 22.71, and that equals 137.4 litres. Okay, so there's more of a traditional stoichiometry question. We're relating the quantity of one thing to the quantity of another using a balanced equation, but we're using PV equals nRT in here. Okay, well there was 3 example calculations. As you know, practice is key with these things. There's no more about gases in this series of 4 films. The last 3 are all to do with percentages, so good luck with those.